Before we get into this, I need to warn you. What you're about to discover has been hiding in plain sight. Planets so bizarre, so violent, so impossibly strange they break every rule we thought we understood. And once you see them, you can't unsee them. We're going to cover worlds hotter than stars. Worlds where it rains molten iron. Worlds drifting through permanent darkness without a sun. Worlds with ring systems so vast they dwarf entire orbits. But that's not even the strangest part. Stay with me. Our galaxy is absolutely full of strange worlds. That shouldn't surprise you. Just look at our own solar system. Rocky planets, gas giants, boiling surfaces, frozen moons, some with rings, some with storms the size of entire planets, worlds with dozens of moons, worlds with none at all, and yet all of that completely ordinary. Because once you look beyond our solar system, things get truly, genuinely weird. NASA has confirmed over 6,000 exoplanets in the Milky Way. Let that sink in for a second. 6,000 worlds orbiting other suns, 6,000 alien skies. Some of them look familiar, many of them don't. Others are something else entirely. Worlds with multiple suns blazing overhead. Worlds where iron vaporizes and falls back down as rain. Worlds with ring systems the size of Venus's orbit. Worlds hotter than most actual stars in the universe. So which ones are the absolute strangest we've found? What wonders is our galaxy hiding? And what might still be out there, waiting to be discovered? Let's find out. When it comes to strange planets, sometimes the weirdness isn't the planet itself. Sometimes it's how the planet moves, specifically how fast it moves around its star. How long is a year on another world? Let's start close to home. Mercury has the shortest year in our solar system. Just 88 Earth days. And here's something that genuinely bends your brain about Mercury. A single day there lasts twice as long as a year. Think about that carefully. 2 full years happen inside every single Mercurian day. If you lived on Mercury, time itself would feel broken. Calendars would be useless. The concept of a year would mean almost nothing at all. But compared to what exists beyond our solar system, Mercury looks positively slow. Most exoplanets we've discovered have extremely short years, and there's a very specific reason for that. It comes down to how we find them in the first place. Giant observatories monitor thousands of stars simultaneously. They watch, they wait, they process. They're looking for a tiny dimming in a star's brightness, a slight dip, almost imperceptible. When a planet passes in front of its star, it blocks a little light. That dip in brightness is called a transit. But here's the catch that limits everything. To confirm it's actually a planet, we need to see the pattern repeat. Multiple transits, regular intervals, regular. If a planet takes 2 Earth years to orbit its star, we need to watch for 2 full years to see a second transit, then another 2 years for the third. That's a long wait for confirmation. So naturally, the planets we find fastest are the ones with the shortest orbits. Days, weeks, maybe a month. The famous TRAPPIST system, one of the most studied planetary systems we know of, has an innermost planet that orbits its star in just 1.5 Earth days. 1.5 days is a complete year. So out of all the thousands of exoplanets confirmed so far, which one has the absolute shortest year? Turns out there's a pulsar with a companion object in an orbit that defies intuition. It could be a planet, could be the collapsed remnant of another dead star. Either way, it completes 1 full orbit in just 48 minutes and 58 seconds. Read that again slowly. A year. In under 49 minutes. How is that even physically possible? The object is extraordinarily close to the pulsar, and it's moving at incredible speed. A neutron star is tiny, maybe 30 kilometers across at most, but its gravity is so extreme it bends light around itself. An object moving fast enough and close enough stays in orbit. The gravity holds it in place even at those extreme velocities. Now technically, a pulsar isn't a standard main sequence star. It's a stellar remnant. So if we want the record for a planet orbiting an actual sequence star, the winner is K2 137b. Its year lasts exactly 4.31 hours. 4 hours and 18 minutes is a complete year. For context, in the time it takes you to watch a feature film, K2 137b completes its entire orbit around its star. The catch, though, is serious. It's orbiting so close that it sits inside the star's outer atmospheric layers. The drag from that atmosphere is slowing it down, gradually, relentlessly. Eventually, the planet will spiral inward and fall into the star. On the other end of the scale, the longest known planetary year belongs to a Jupiter mass object, drifting in a remote, cold, distant orbit. Its year lasts approximately 1 million Earth years. 1 million. We've been modern humans for around 300,000 years. That planet hasn't even completed a third of a year during the entire history of our species. But for some planets, asking about their year doesn't even make sense, because some planets orbit more than one star. Our solar system is beautifully simple. One star. Everything else orbits it. Most planetary systems across the universe work the same way. But not all of them. Some systems have 2 stars orbiting each other, 3, 4, 5, even 7. And in those systems, a planet's relationship with time, light, and warmth becomes extraordinarily complicated. Can a planet actually orbit multiple stars at once? The answer is yes, but it depends entirely on the configuration. Multiple star systems tend to organize themselves hierarchically, layers of gravitational relationships nested inside each other. This structure keeps the whole arrangement stable over millions of years. Without it, stars would eventually be ejected from the system entirely. Binary stars are the simplest case. 2 stars orbiting each other around a shared center of mass called a barycenter. Their orbits are typically elliptical. The more similar their masses, the more symmetric the orbits appear. With 3 stars, the arrangement gets more layered. 2 stars form a tight binary pair, acting almost as a single gravitational object. The third orbits that combined pair from a much greater distance. Add a 4th star and you can have 2 binary pairs orbiting each other around a shared center of mass, or a binary plus a solo star, with all 3 orbiting a 4th. 5, 6, 7 stars, same layered logic, more complexity at each level. So where do planets actually fit into all of this? A planet orbiting just 1 star inside a 7-star system would technically have 1 sun. A planet orbiting a binary pair sees 2 suns in its sky, 2 different colors, different sizes, different trajectories across the sky, sometimes close together, sometimes separated by a visible gap. And a planet orbiting an entire 7-star system from the outside, 7 suns, 7. Let that image fully form in your mind. Imagine standing on a rocky, dusty surface somewhere in that system. You look up. 7 different points of light compete for dominance in the sky. Some burning white, some warm orange, some deep, smoldering red. Some clustered so close together they blur at the edges. Others clearly separated, moving on their own visible trajectories. That's not science fiction. That's just physics working exactly as it should. And this raises the practical question nobody asks enough. What would it actually be like to live on a planet with multiple suns? Would seasons make any sense? Would there be a real day and night cycle? Would life as we know it even be possible? The answers vary enormously depending on which types of stars are involved. Let's say we keep our own sun exactly as it is, and we add just 1 second star, the smallest type available, a red dwarf. Even a red dwarf, with just 7.5% of the sun's mass, would have enormous consequences for Earth. From our perspective, the red dwarf would appear to orbit our sun. There would be moments when it transits in front of the sun, others when the sun eclipses it completely. The sky would never look quite the same twice. Our year would shorten significantly. The combined gravitational pull would require Earth to move faster. The temperature increase would be noticeable immediately, possibly deadly depending on the orbit. But here's the thing that nobody usually emphasizes about red dwarfs. They produce flares. Enormous, violent eruptions of radiation, far larger than anything our sun generates. These flares would knock out satellites without warning. They would trigger spectacular auroras across the entire globe. They would send electromagnetic pulses worldwide. Our entire electrical infrastructure would be under constant, serious threat. Make the second star larger, and things get progressively worse. Ultraviolet radiation intensifies dramatically. You'd cast 2 shadows most of the time. Looking at the sky directly would require serious eye protection. Make it a blue supergiant? There is no habitable zone anywhere in that system. Blue supergiants can be 150 times the mass of our sun, millions of times more luminous. Their stellar winds would strip our atmosphere bare in a cosmically short time. And if that supergiant goes supernova within 50 light-years, that's an extinction-level event. No question. But here's where it gets genuinely interesting. Binary stars can orbit each other at enormous distances, thousands of years for a single orbit, in extreme cases separated by more than a light-year. In these wide binary systems, each star can have its own independent planetary system. Earth could orbit one star normally. The second star would appear in our night sky. Bright and beautiful, but far enough away to cause minimal disruption. The first planet ever confirmed orbiting a binary star was Kepler 16b, spotted by NASA's Kepler Space Telescope in 2011. Scientists immediately nicknamed it Tatooine. It's not a desert world, though. It's a gas giant about 0.3 times the mass of Jupiter. Its orbit around both stars simultaneously has fascinated researchers ever since. They use it to study the three-body problem, the complex, partially unsolved mathematics describing how three gravitating objects interact simultaneously. Since Kepler 16b, several similar worlds have been confirmed. They're not rare. More than half of all stars in our galaxy have at least one stellar companion. And yet, living on any of those worlds would be far from easy. No wonder Luke always wanted off Tatooine. But at least those worlds have suns keeping them warm. What about planets that have no star at all? There are planets drifting through the galaxy in complete, total darkness. No star, no light, no warmth from above. Just endless, frozen, absolute black. These are called rogue planets, interstellar planets, wandering worlds, and they represent one of the deepest, strangest mysteries in modern astronomy. We don't fully understand where they come from. One theory, they started inside normal planetary systems, like ours. Got too close to a massive neighbor during the chaotic early years of the system. Got flung outward by gravitational interactions, launched into interstellar space at tremendous speed. Following that logic, our own early solar system may have had additional planets that were hurled outward billions of years ago, now wandering alone far beyond any star's reach. Another theory. Some rogue planets are failed protostars, clouds of gas and dust that almost became stars. They gathered enough material to form a planet-sized object, but never quite enough to ignite nuclear fusion in their cores, stuck forever in a cold, dark, intermediate state. Here's where the scale becomes genuinely hard to process. Scientists estimate there could be billions, possibly trillions, of rogue planets in the Milky Way alone. Trillions. And we've found almost none of them, because detecting a dark object against the infinite darkness of space is extraordinarily difficult. They emit no visible light, they reflect nothing. They orbit nothing. From across the galaxy, they're essentially invisible. So how do you find something completely invisible? The answer is a technique called gravitational microlensing, one of the most elegant detection methods in all of science. Einstein predicted the basic underlying phenomenon in 1936. The concept is both simple and deeply profound. Light travels in straight lines through empty space, mostly, but space itself curves around gravitational mass. When something massive sits between us and a distant light source, it bends that light around itself, acts like a cosmic lens. The distant background object appears brighter than it should, because the foreground object's gravity is redirecting photons toward us. Focusing them like a glass lens focuses sunlight. For truly enormous objects like galaxy clusters, this effect is dramatic and visible. You've seen those famous Hubble Deep Field images. Distant galaxies smeared into glowing arcs, rings of distorted light. That's gravitational lensing at its most extreme. For smaller objects, individual stars, planets, the effect is subtle, a tiny, fleeting brightening, but measurable with the right instruments. When a rogue planet drifts across the line of sight to a distant background star, see that star briefly brightens, not a dip in light, a peak, a short, sharp spike lasting hours or days, then gone. That's the microlensing signature of a rogue planet. The planet briefly reveals itself against the background light, then vanishes back into the dark. Current ground-based programs, KMTNet, MOA Supermash and others, have identified 22 rogue planet candidates to date. The most exciting of them is designated Mowgli 2012 BLG 1323. If confirmed, It will be the smallest rogue planet ever detected, with a mass approximately equal to Earth's. Think about that for a moment. A planet the size of ours. No orbit, no star, no direction, no destination. Just drifting silently through the interstellar void. Alone. Forever. What would it actually be like to be on a rogue planet? Completely dark, obviously. Utterly, profoundly, absolutely dark. Without any nearby star, the only light comes from the impossibly distant, cold points of faraway suns, billions visible, none providing meaningful warmth. Standing on the surface would be like standing at the bottom of a deep ocean at midnight with no lights at all. Just blackness in every direction. You'd naturally assume such a world would also be frozen solid. Temperatures near absolute zero. A dead, inert ball of rock. But here's the part that genuinely surprises people. Without a nearby star, there's also no nearby stellar wind, no stream of charged particles constantly bombarding the atmosphere, no radiation gradually eroding the atmospheric layers. A rogue planet could retain its atmosphere almost indefinitely, held in place by its own gravity, insulated by its own density. A 1999 research paper made a striking suggestion. A rogue planet with a hydrogen-rich atmosphere could retain enough internal heat to sustain liquid oceans, not from sunlight, never from sunlight, from the planet's own molten core, slowly radiating upward over billions of years, combined with the thermal insulation provided by that thick, heavy atmosphere pressing down from above. Life on such a world would be radically different from anything on Earth's surface. No photosynthesis, no sunlight to drive it. Instead, chemosynthesis, drawing energy from heat and chemical reactions rising from below, similar to the bizarre ecosystems we've found near deep-sea hydrothermal vents right here on Earth. Tube worms, extremophile bacteria, organisms that have never needed sunlight to survive. No forests, no seasons, no sunrise. Just warm, dark oceans kept barely alive by geological heat, radiating from within. It's a universe profoundly different from the one we usually imagine, but potentially the universe we actually live in. Now let's talk about a world that is the complete opposite of dark and cold. WASP-76b was discovered in 2013 as part of the Wide-Angle Search for Planets program. It immediately intrigued researchers, but in 2020 the ESO's Very Large Telescope revealed one specific detail that reframed everything. The rain on this planet isn't water, isn't acid, isn't ammonia, it's iron, liquid iron droplets, falling from the upper atmosphere like a metallic storm. How does this work? WASP-76b is a gas giant far larger than Jupiter. It orbits its host star in just 1.8 Earth days. That proximity means the planet is almost certainly tidally locked. One face permanently aimed at the star, one face permanently turned away. Day side and night side. Fixed forever. The dayside temperature reaches approximately 2,400 degrees Celsius. At that temperature, iron doesn't just melt, it vaporizes completely. Iron becomes gas, rising into the upper atmosphere, being swept up by ferocious wind systems. Those winds carry the iron vapor from the dayside across the terminator, the boundary between light and dark hemispheres, to the cooler night side. On the night side, temperatures drop to around 1,500 degrees Celsius, still extraordinarily hot by any standard we're familiar with, but just cool enough for iron vapor to begin condensing into droplets, liquid iron droplets, falling downward through the atmosphere. Iron rain. When those circulation currents loop back around toward the morning side of the planet, the iron signature disappears from measurements. It has sunk deeper into the atmosphere, out of reach, gone until the cycle repeats. The instrument that detected this, the espresso spectrograph on the VLT, marked the first time atmospheric variations like these had ever been directly observed on an ultra-hot gas giant. It will not be the last world we find like this. Planets hot enough to rain metals are out there, and we're building better tools to find them, but WASP-76b is not even close to the hottest planet we've ever found, not in the same league. Scale up the heat, way up. Kelt 9 is a blazing star with a surface temperature of 9,700 degrees Celsius, nearly twice the surface temperature of our Sun. It burns white-hot and furious, and orbiting it just 5 million kilometers away, 10 times closer than Mercury orbits us, is Kelt 9b, a gas giant almost twice the size of Jupiter, 3 times Jupiter's mass, locked in a scorching, relentless orbit around its merciless host. The measured temperature of Kelt 9b, 4,300 degrees Celsius. For context, the average red dwarf star burns between 2,500 and 4,000 degrees. Kelt 9b, a planet, is hotter than most stars in the galaxy. Its hydrogen atmosphere is being actively blasted into space, stripped away layer by layer, at an estimated rate of 100,000 to 1,000,000 tons of hydrogen per second. Every second. Some of that escaping gas gets pulled back toward Kelt 9 by the star's gravity, recaptured, consumed. Eventually, Kelt 9b's atmosphere will be entirely gone. What remains will be the bare core, exposed directly to the inferno. And when Kelt 9 expands in approximately 300 million years, the planet will be consumed entirely. Right now, the surface environment of Kelt 9b is so energetic that chemical bonds cannot hold. Water molecules shatter. Carbon dioxide tears apart. Even simple compounds cannot survive. There are no molecules on Kelt 9b, just individual atoms flying apart in superheated plasma. Nothing has ever lived there. Nothing ever will. But this raises an interesting question. If some planets are hotter than actual stars, can some planets be physically larger than their host stars? Here's what I need you to keep in mind before we get to the final section, because the next part of this story involves a planet that should not exist, a world that survived something that absolutely should have destroyed it. And then there's a planet with a ring system so large it almost defies measurement. Keep watching. When we picture a solar system, we assume the star is the biggest object in it, a blazing, dominant center, everything else circling around it. That's generally true, but certain categories of object in the universe break this assumption completely. For a star to be a star, it must fuse hydrogen in its core. That requires a minimum mass, approximately 8% of the Sun's. Below that threshold, the object becomes a brown dwarf, a failed star. Massive enough to glow faintly from gravitational compression, but never massive enough to achieve true nuclear fusion. Below brown dwarfs in terms of mass are planets, moons, asteroids, and dust, the building blocks. Now consider what happens to stars at the end of their lives. Some of the most massive ones collapse catastrophically. The inner core implodes. The outer layers explode outward in a supernova. What remains is a neutron star. 1 to 2 solar masses squeezed into a sphere roughly 30 kilometers across. 30 kilometers, about the distance across a large metropolitan area. Compressed into that space, the full mass of an entire star. Gravity on a neutron star is so intense that light itself is bent by its surface. A teaspoon of neutron star material would weigh hundreds of millions of tons on Earth, and planets orbit neutron stars. We've confirmed this. Since a neutron star is only about 30 kilometers across, even a modest planet, hundreds of kilometers wide, is physically larger than its host star. A mountain orbiting a marble, in terms of volume. Then there are white dwarfs. White dwarfs form from stars like our Sun, stars that were never massive enough to produce a supernova. When such a star exhausts its hydrogen, it expands dramatically, becoming a red giant, sometimes hundreds of times its original diameter, engulfing inner planets, vaporizing them. Eventually, the outer layers drift away as a glowing planetary nebula. What remains is the hot, dense core, a white dwarf, roughly the size of Earth, but with the compressed mass of a full star. Some planets survive the red giant phase, far enough out that the expanding star never fully reached them. These planets continue orbiting the white dwarf after it forms, orbiting something smaller than themselves. We found a confirmed example. The system is called WD 1856. The planet is WD 1856b, detected by NASA's TESS observatory. Here's what makes this discovery remarkable. The planet orbits the white dwarf at a quite close distance. Too close. During the red giant phase, the expanding star would have extended well past where the planet now sits. The planet should have been vaporized, engulfed, destroyed, and yet it's there, orbiting, stable, intact. How? The leading theory is migration. The planet originally occupied a much wider orbit, safely beyond the expanding star's reach. After the stellar expansion phase ended and the white dwarf formed, gravitational interactions with other bodies nudged the planet inward. Over millions of years, into the orbit it occupies today, a planet that outlasted its star's expansion and death. Now calmly circling the cold, dim remnant, that's one of the most resilient things we've ever found in the universe. For normal main-sequence stars, finding a planet larger than its host requires searching at the extreme edge of stellar classification. The smallest main-sequence stars are red dwarfs, sitting right at the minimum mass for hydrogen fusion. Technically stars, barely. Vastly outnumbered, roughly 85% of all stars in the Milky Way are red dwarfs. The smallest of these dim, quiet stars have radii around 70,000 kilometers. The largest known gas giant planets can reach 2 or even 3 times that in radius, a planet physically larger than the star it orbits, quietly circling something smaller and dimmer than itself. One of the best candidate systems is VHS 1256-1257. The companion object here is distant enough from its host star to be directly observed with a powerful telescope. That's unusual. Most exoplanets can't be imaged directly. But the challenge remains. Without a precise radius measurement, we can't confirm it definitively. Margins of error on both sides. Either object might actually be a brown dwarf, which changes the entire classification, so definitive proof remains elusive. But the mathematics strongly suggests confirmed cases are out there, waiting for better instruments to find them. The current leading candidate for the largest planet ever discovered is ROX 42Bb. Its radius is estimated at approximately 3 times that of Jupiter. For scale, Jupiter alone could contain over 1,300 Earths. ROX's 42Bb could fit 3 Jupiters across its diameter. Other strong candidates include DH Tau b and HN Peg b, all of them pushing the boundary between planet and brown dwarf. Enormous, strange, difficult to classify. Now let's end with the discovery that might be the most visually spectacular in the entire history of planetary science. If it's confirmed, the object is called J1407b, and it may be the first exoplanet ever found with a Saturn-like ring system, except this ring system would be incomparably, impossibly larger than Saturn's. Here's the context you need. Saturn's rings are beautiful, iconic, familiar. They extend outward roughly 282,000 kilometers from the planet's center, impressive by solar system standards. J1407b's rings, if the measurements are correct, cover an area more than 40,000 times greater than Saturn's, 40,000 times. Those rings would extend outward as far as Venus orbits the Sun, hundreds of millions of kilometers of ring material wrapped around a single planet. Imagine looking at a planet wearing rings the size of a solar system. If you stood on another world nearby and looked up, the rings would arc across your entire sky, from horizon to horizon. Bright bands of light and dark shadow stretching overhead in every direction, multiple distinct ring structures, gaps between them, casting structured shadows on the landscape below. This wasn't discovered by direct imaging. It was found through a transit event in 2012. Researchers analyzing brightness data from the SuperWASP survey noticed something extraordinary in the records. When J1407b passed in front of its host star, it blocked 95% of the star's light. 95%. For comparison, when Jupiter transits a star, it blocks roughly 1% of the star's light. Its rings block even less. J1407b blocked 95%. And the dimming lasted for weeks. Not hours, not days, weeks. The complex pattern of brightness variations throughout that long transit allowed astronomers to map a detailed ring structure. Multiple distinct ring bands, separated by clear gaps. Inside those gaps, evidence of at least one small moon beginning to form, its gravity carving out a clean lane in the ring material, exactly the way moons carve the Cassini division in Saturn's rings. This indicated the rings were not permanent. They are evolving, thinning, concentrating into bands, gradually destined to coalesce into a family of moons around the planet. But right now, if the interpretation is correct, Standing anywhere in that system with a clear view of J1407b? The sky would be unlike anything in our imagination. There is a problem, though a significant one that has kept scientists cautious. J1407b's orbital period is estimated at around 10 years. Since the initial transit in 2012, no equivalent dimming event has been observed from the same star. None. Every year without a repeat adds to the uncertainty. Two possible explanations are on the table. First, the original event was an isolated encounter. A rogue brown dwarf or free-floating protoplanetary disk happened to drift past the star by coincidence. J11407b as an orbiting planet doesn't actually exist. Just a cosmic coincidence, a one-time alignment. Second, J1407b is real. It's in orbit. But the ring system is significantly thinner than initial models assumed. Thin enough that subsequent transits, viewed from a slightly different orbital geometry, cause far less dimming, less noticeable, easy to miss. The mystery remains completely open, unresolved, and that is perhaps the perfect note to close on. We've found worlds hotter than actual stars, worlds drifting forever in permanent darkness, worlds where iron condenses and falls as metallic rain, worlds orbiting multiple suns simultaneously, worlds that survived their star's death and still orbit the cold remnant, worlds that might be wrapped in rings larger than entire planetary orbits. And we've found all of this in just 6,000 confirmed exoplanets, out of what astronomers believe could be hundreds of billions in the Milky Way alone. We have barely started looking. Every new telescope adds resolution we didn't have before. Every new technique reveals signatures we couldn't detect. Every new mission uncovers things we didn't even know to search for. The galaxy isn't just full of planets, it's full of things we don't yet have the language to describe. So here is the question I want to leave with you. If we've already found iron rain, worlds hotter than stars, ring systems larger than Venus's orbit, in just our first 6,000 confirmed worlds out of potentially hundreds of billions, what is waiting in the rest? What is out there that we haven't even imagined yet? What will the next generation of telescopes reveal that breaks everything we currently think we know? I genuinely want to hear what you think. Drop your wildest theory in the comments below. Let's see who predicts the next impossible discovery. And if this expanded your sense of how strange our galaxy really is, share it. Someone in your life needs to know that the universe is this unbelievably, wonderfully weird.